we're not going to talk about community detection. Another name for it is clustering network data. So we're talking about clustering, something that I hope you are already familiar with. Clustering is an unsupervised learning method. When we don't have labels, sometimes we just create groups of data points that are similar to each other and call them clusters. For example, k-means is a very simple algorithm for clustering tabular data. But for network data, if the data we have is just about connectivities, if it's just about whether different entities know each other or not, those sort of things, then we need community detection. So community detection for network data would be analogous to k-means for tabular data. And tabular data is just data that you can have in a table. For example, the data from your first project was tabular data. All right, so this is a very famous example in community detection. This is a social network. Each node is a person, and this social network is a karate club. So this was a university club. Each node is a club member, and the edges represent interactions between these club members outside of the club. Then node 1, I believe, was the instructor of the club, and node 34 was the administrator of the club. And at some point, so this was an anthropology study. Some anthropologists studied these people, this group of 34 people, for several years. And then sometime during the study, there was a conflict between the instructor, between node 1, and the administrator, node 34. And then each of these people tried to pretty much attract as many people to their side of that conflict to kind of alienate the other person. And as the relationship between these people outside of the club meant that they could talk to each other outside the club, this anthropologist made a prediction about what's going to happen to this club. The anthropologist looked at the connectivity patterns of how these people interact with each other outside of the club and predicted that there's going to be a split in this social group, and the split is going to be on this line. This is the line that has the maximum flow of information. So this is a minimum cut, maximum flow line for this graph. You don't need to worry about that part, but this is the connectivity patterns. It was rather obvious that the club is going to break apart into two groups. And just based on the connectivity patterns, this anthropologist predicted that the future grouping of these these people will be based on this line. So he predicted, Zachary Wayne, who was the anthropologist, predicted that this would be one group and this would be another group. And this is a study from, I guess, 60s or 70s. And actually, then later it was shown that these predictions were almost exactly correct, which is mathematically impossible, almost impossible, because essentially for each node, you have two possibilities. You don't have any other information. You only have the structure of the network. For each node, you have two possibilities. So for 30 nodes, when you have 34 nodes, it means there are 2 to the power 34 different partitions into two groups. So if you just randomly predict what would be the grouping, we would be correct by this likelihood, 1 over 2 to the power of 34, which is essentially 0. And this is not a prediction that uses a lot of information. We don't have like traditional tabular data for making predictions on what's going to happen. So this anthropologist just looked at these patterns and made prediction that this would be how the group will split. And except for one node, except for node number 9, everything in the prediction came out to be true, which is quite remarkable. And that's the reason why this example is very famous. So the community assignment, so these two are essentially the communities. The communities were predicted using a graph maximum flow algorithm. So when you have a graph, you can find the cut. So a cut, this red line is a cut, is essentially a collection of edges that if you cut them, the graph will be disconnected into two components. So among all the possible cuts, this anthropologist found the cut that is associated with the maximum flow of information, assuming that every two persons in this network is talking to the other person. So this is the connection between the social science part of this and the algorithmic part. So it is kind of expected that as finding allies to your side of the argument involve talking to people, talking to other club members, looking at the maximum flow where there's maximum flow in the graph would be a suitable way of, a very accurate way of making predictions about what's going to happen. Yes?
Here, finding the maximum flow is the only criteria for grouping the points.
Yeah.
So there's another criteria like density
No, it was just maximum flow. So it was, they had, I mean, this anthropologist had the structure of this graph and just assumed that there's information flow between every node, right? And then the graph cut that has the smallest number of edges in it, and those edges have the maximum flow of information, was the answer to predicting where the group is going to split.
And in this picture, all of the edges have the same group?
Yeah, all of them have the same, because we don't have any information. The only information is that we know that node 27 and node 30, they interact with each other outside the club. That's the only thing we know. So from the anthropological study, he had asked these people, he had asked number 27, who are the people you would talk to outside of the club? And person number 27 had told Zachary Bain that they are node 30 and node 34, right? So that's how he had the information on this graph.
So you mean node 1 and node 34 should be in a different group?
Node 1 and 34 were two opposite sides of a huge argument. So they had a disagreement, a very fundamental disagreement, which was breaking the club apart into two. So it was clear that 1 and 34 would be in two different clusters. The question was, what would be the other people who would join 1, and who would be the people who would join 34? Eventually, people in the blue community formed a new club, and people around 34 in green, they found a new instructor and created a new club. So this was a social group that break into two. And when we think about clustering network data, this is the ideal case of understanding how a social system breaks into two. And the idea of clustering is also about breaking entities of a network into groups. So this was quite a remarkable prediction for that time, especially because it's a prediction based on no information other than pairwise interactions between people. Yeah?
So the distances between the nodes is kind of like arbitrary?
The distances?
Yeah.
Oh, the distances are arbitrary, yes. So you can, I should have cleared this, that a graph is just about this connectivity pattern. So this red triangle, if it is 1, 2, 3, I can also draw it like this. There's nothing special about their positions. This is the same graph. So the position of nodes is totally flexible and meaningless in a graph. Yes?
Something for the question, but in the graph, there's also another line which provides more maximum in the graph.
Is there another line?
Yeah.
Where is it?
Between 10 and 31, 9 and 34, 33 and 29 and 25 and 30.
So another cut
Yeah.
that has higher flow.
Yeah.
Well, we can discuss that, but this is a very famous example. So what you're saying is that
I counted the number of the edges have been cut. This line is around 10. That one's 13.
this is a minimum cut. A maximum cut is certainly not this. A maximum cut, I can just give you one cut with more edges. Maximum cut is not really that relevant. This is a cut, I'm cutting the edges. This is a cut that cuts more edges than the red one. This doesn't mean anything. It was finding a minimum cut that is associated with maximum flow. And that part, min cut max flow is something, is kind of a peripheral sort of topic. What I'm trying to say is that for understanding the social system and making predictions on it, this researcher just used graph theory. And the prediction was remarkably close to the reality. Despite that, there was almost no information used in the prediction. It was just a connectivity pattern. All right, so then this process of starting with a graph like this as input and then finding clusters of nodes is called community detection. So the input is something like this. The method is an algorithm, a community detection algorithm or a network clustering algorithm. And the output would be a partition of nodes into communities. So this would be the output. So this process from having an input in black and white and obtaining an output like this is called community detection. That's what we're going to talk about. Because there are many different ways to develop a community detection algorithm. And as this is not supervised learning, it's not that straightforward which algorithm is better than the other. Because we cannot just measure something like classification error rate or accuracy or F1 score and so on. So this is an unsupervised learning task. It has some similarity to k-means because it's clustering. And there are different ways of doing this. And we're going to learn, about performance of some algorithms, some community detection algorithms. So the process of starting from this input and getting this output is called community detection. And the goal is essentially grouping. So so your name is Junda, right? So back to the question from Junda, the goal is grouping tightly connected nodes into clusters or communities, which can be gently or loosely connected to the rest of the network. So now finding this partition is not for, I mean, it involves some objective. The objective is that we can see that these nodes are highly connected to each other, but loosely connected to the rest. So let's call this one community. So it is based on connectivity patterns. So ideally, a community detection method, which is designed for this goal, should give us communities such that most of the edges are within communities and relatively few edges are between communities. All right. So this idea of optimization-based community detection is quite intuitive. So as the input, we have a graph. We represent a graph like this: G of V and E. G is the graph, is the network. V is the set of nodes or vertices. So for this graph, V is 0, 1, 2, and 3. This is set of vertices of this graph. E is the set of edges of this graph. So we can represent it like pairs of nodes. So you can see that there's an edge between 0 and 2. So I just represent it like a tuple. 0 and 2, 0 and 3, and 1 and 3. So this graph, another version of representing it is like this: G of V and E. Sometimes we write it like this: G equals this. And V is set of nodes, E is the set of edges. So already you know 3 ways of representing a graph: by its visualization, by its adjacency matrix, and by its sets of nodes and edges. So even a graph as input, we want to find a partition of V, a partition of the node set, into V1, V2, all the way to V sub C. These are the communities, such that a certain objective function is optimized. So in the case of Zachary Karate Club, it was optimizing minimum cut maximum flow. This is from this study in 1977 by this anthropologist, Wayne Zachary. And in 2006, this physicist, Mark Newman, suggested a new objective function for this problem, which is called modularity. So a modularity-based community detection would be the task of finding a partition for a graph such that the modularity of that partition, this is the partition and that graph, so modularity is a function of both graph and the partition, such that modularity is maximized. And modularity kind of encapsulates this idea that edges within communities should be more than edges between the communities. Not just more, but the idea that a partition that has most of the edges within communities rather than between communities is a better partition than a partition that has most of the edges between communities. So for a given network, there are many partitions. So this is the same network. I can create this partition. I can say this node and this node in one group. This node and this node and this node in one group. And then, I can just put things that are not, neighbors of each other. So between these two partitionings, one of them is better than the other. So the partition, so between these two partitions, the one on top and the one in the bottom, one of them is better. How do we quantify a partition to be better than the other? Is based on modularity. So for example, the modularity, which we represent with Q, the modularity for this purple partition is, let's say, 0.1. The modularity for this partition is 0.8. So when we go over all different ways that the nodes can be grouped into communities and find the partition that maximizes Q, would be a community detection algorithm. All right, would be so modularity, back to the question from Tiggy, takes into account the degrees of the nodes, their connections, and a resolution parameter. So degree of the nodes, for example, node 2 has a degree of 1, node 0 has a degree of 2. And modularity is calculated like this. For every pair of nodes, regardless of whether they are connected or not, for every I and j, we look at the adjacency matrix. We look at the entry in the adjacency matrix, which is either 0 or 1, telling us whether there's an edge or not, and we subtract degree of I, degree of j, divided by 2m. And there's also some resolution parameter. This resolution parameter tells us essentially how much we care about this second part of the formula.
So what's M?
Sorry?
What's M?
M is the number of edges. So the cardinality of the node set is n, the cardinality of the edge set is m. So usually a graph V and E has n nodes and m edges. So we divide by 2m to kind of normalize these degrees. So this is just an objective function. This means that for this network, the matrix B, this is the modularity matrix. Modularity matrix. For this network that you see in here, the modularity matrix is this. This is the modularity matrix where the resolution parameter is set to 1. It's a very simple modularity matrix. So this graph data kind of translates into this matrix. And then in this matrix, when we put nodes in one cluster, the entries associated with those nodes will be added to the objective function. So the objective function is like this. It's very complicated, but don't let the formula scare you, because the objective function is essentially something like this. We're trying to maximize modularity. Modularity is based on these Bij entries, which are these values in this matrix. And whenever I and j are together in one cluster, their B and j value will be added to the objective function. So we want to maximize Q, and these are the things that we can put in Q. So they are positive ones. For example, this is positive, this is positive. This means that if we select a partition such that 0, 1, 2, 3, such that 0 and 2 are together, because you can see that this is positive and relatively large, and 1 and 3 are together, then these positive things will be added to the objective function. So we have a matrix. Every entry from this matrix that you select talks about what is the benefit or what is the cost of putting nodes at the row and column of that entry in the objective function. So this value says, all right, this value says if you put 0 and 1 together, it has a cost of this much because it's negative. This value says if you put 0 and 2 together, you have a reward of 65, 0.65. This value says if you put 0 and 3 together, you have a reward of 0.33. And we solve this with an algorithm. The algorithm looks at different possibilities of putting nodes together that would maximize the reward that we can get from this matrix. And there's also conflict between rewards and penalties. Because, for example, there are situations where you want to put 0 and 2 together, 0 and 1 together, and you get rewards from each of these assignments. But you get a penalty from putting 2 and 0 together. And also on the figure, you can see that because there's an edge, there's a reason to put 0 and 2 together. There's also a reason to put 0 and 3 together. But when you put both 0 and 2 together, 0 and 3 together, you're also putting 2 and 3 together, which don't know each other. So nodes that are not connected give you a penalty. So modularity maximization is about finding the kind of compromise between all these possibilities. So it's an NP-hard graph optimization problem, meaning that solving it exactly is notoriously hard. But then for this network, actually the partition that maximizes the objective function is this. So in this matrix, we have positive values whenever there's an edge between I and j, and for pairs of nodes for which there's no node, there's no edge. For pairs of nodes for which there's no edge, which we call non-edge pairs. For example, 0, 1 is a non-edge pair because there's no edge between 0 and 1. There's a penalty for them. These values are always negative. And then the partition that maximizes modularity for this network is actually this. This is based on modularity. This is the best way of partitioning the nodes into groups. Why is that the best way? This is the best way because maybe naively we may think that everything is connected to everything, so let's just put everything in one cluster. If we do that, we also accept the penalty of putting these two together which are not connected, one penalty, putting these two together which are not connected, putting these two together which are not connected, putting these two together that are not connected. So we accept 4 penalties for the sake of getting the benefits from these edges. So this is about edges and non-edges. That's the whole point. The problem is very, very fundamental and simple. That's why we see it in all fields of science. So this is not just about social networks. We have it everywhere. We have it in medicine. We have it in physics, biology, finance, electronics. So the reason, another explanation why this is the optimal partition is that for node 2, everything that node 2 has in this system is the edge between 0 and 2. That's why the cost of cutting edge 0, 2 is very high. The same for the edge 1, 3, the cost is very high if you want to cut that edge. If you want to cluster, form the cluster such that that edge would be between two different clusters. But the edge between 0 and 3 is not kind of all the things that these nodes have. Nodes 0 and 3 also know other people in the system. So this is as if there's a kind of a attraction between two nodes that are connected, and there's a kind of repulsion between any pairs of nodes that are not connected. So there are kind of forces in two different directions. We want to ideally put things that are connected together and put things that are not neighbors separate. That's why eventually we need to make compromises, and the best compromise is this, according to modularity. Question?
So can I just confirm, so what the algorithm is going to do is we want to penalize edges between communities, so minimum edges between communities. So we reward least edges between communities, and we also reward most edges within a community, and they're both equal. And we're trying to like.
No, we reward modularity. We reward this. This thing can be positive or negative for a pair. Whenever it's positive, it's ideal for I and j to be in the same cluster so that we benefit from the positive term that will be added to the objective function. Whenever this is negative, we ideally want to put this in two different groups so that we don't get the penalty. So everything is about Bij. The penalty and the reward, both of them are in Bij. Yes? This one? Delta is the this tells us whether I and j are together or not. So modularity is a function of both the graph and the partition. So if in partition X, I and j are together, delta becomes 1.
So kind of like an adjacency matrix.
Yes.
Instead of an adjacency matrix, it's the partition.
Yeah, it's a function. Yes. But we can, yes, it is based on the partition. Exactly. Yes.
Would you say that another way of expressing this equation would be, so the term in parentheses is Bij, and basically what you're doing is for every ij pair that's part of, like you're summing across all partitions, and then within each partition, you're summing across all pairs of nodes, the modularity for the pairs. So it would be for like, the summation of C is equal to, C belonging to X.
Yes. We can also write it based on communities.
Okay.
Here we're writing it based on pairs of edges, pairs of nodes. We go over every possible pair of nodes, and essentially it's over a pair of nodes that are together in one partition, because whenever they are not together, here delta becomes 0, and this thing will not be added to the objective function. That's why I wanted to replace, I just included this so that you know that modularity has a very ugly formula, but my purpose was for you not to look at this formula and instead look at this. Modularity is simply a sum, and the sum is based on how we form the partition. Whenever two nodes are together, Bij is added to the objective function. Whenever they are not together, Bij is not added. And then Bij is sometimes positive, sometimes negative. So ideally, whenever it is positive, we want to put I and j together so that we get the reward in the objective function. Whenever it is negative, we don't want to add it to the objective function. Yes?
So we're back to the definition of Bij. Just trying to confirm what it means.
Yes,
So Dij would be
degrees.
the number of connections. So if we're looking at node I and j, how many like edges they each have, right?
Yeah.
So what is Aij?
Aij is whether those two nodes are connected or not. So let me just write B of 2 and 0. B of 0 and 2, they are connected. So it would be 1 minus, and let's say here for simplicity lambda is 1, 1 minus degree of 2, which is 1, degree of 0, which is 2, over 2 times m. There are 3 edges, so 2 times 3. B would be 1 over 1/3, so it is 0.67. 0 and 2, 0.67. So, yes, and what happened in the end? We actually put them together because there's a substantial reward for putting 0 and 2 together.